Hello, welcome to the second dev workshop. A few weeks ago, we have done our first dev workshop where we went through some of the basic features of Rough, the programming language, the SDK, the CLI build tools, and we built a simple dApp together, a token faucet. That was a lot of fun. In case you haven't participated in the first dev workshop, the video is available on YouTube from here. And the code from the first dev workshop is also available on GitHub, which you can use as a reference. One of the feedback that we got from the first workshop was that it was a little bit too long. It's almost like 2 hours. So this time we're going to do stuff a little bit differently. We will split this workshop into 2 sessions, and hopefully each of the session will be a little bit shorter. So the goal of this workshop is to re-implement the smart contract part of a dApp called Friend.Tech. And the reason that we picked Friend.Tech is because, number one, just in case you don't know, Friend.Tech is a quite popular dApp in the crypto space in the past month. I have digged up some numbers from Twitter. So according to this tweet thread, it basically generates like 500K in protocol revenue every day, which is like a lot of money. And when it comes to the number of transactions, it accounts for around 80% of all transactions on Base, which is like a layer 2 for Ethereum, built by Coinbase. So this is actually a quite popular dApp. That's reason number one. And the reason number two is that even though this is a quite popular dApp, the smart contract part of it is actually not too complicated. So here we're looking at the smart contracts of Friend.Tech on Base skin. As you can see, they have a lot of ETH in it. And here is the entirety of the smart contract for Friend.Tech. And this part deals with the ownership. The meat of the contract is from here to here, so it's not too long. So yes, the fact that it's not too complicated is the second reason we picked it, because we feel that we can try to understand it in a matter of minutes, hopefully like definitely less than 10 minutes. And the third reason is that even though this contract is not too complicated, it's still sophisticated enough for us to demonstrate some of the features that we want to demonstrate for Ralph, namely like subcontracts and also like an asset permission system. So yeah, it's not too complicated, but it's sophisticated enough. That's the third reason for that we picked Friend.Tech. So before we dive into the smart contract for this, perhaps it makes sense for us to try to understand what really is Friend.Tech from the application perspective. So what it does is that actually, according to them, it's like a marketplace for friends. So what does it really mean? It means that as a like an influencer or like a celebrity of some sort, basically it allows your fans to buy your share, and once they own your share, they can sell it too. So it's almost like buying shares for a company. So if you buy in the very beginning, because the interesting part of this is that the price of the share has a direct relationship with the number of outstanding shares. So if you're a popular person with a lot of share, your share will like worth more, which means that if you as a fan, if you get in early, you will get, when the number of outstanding share is lower, you'll get a cheaper price. And once the number of the size of the fan base grow bigger, number of outstanding shares grow, you can potentially sell your share for a profit. And as the owner, every time as a celebrity or like the crypto influencer, in this case Kobe, if any of the fans buys or share or sell his share, he'll get like 5% of the what they call subject fee, because the celebrity or crypto influencer in the Friend.Tech terminology is called a subject. So he'll get a 5% subject fee, which means that Kobe in this case will have like incentive to maintain his fan base, because as long as the fan base exists, as long as there's like trading among all the fans, then he will get money. He'll get 5% of the subject fee. And as a protocol, whenever there's like a trade, the protocol gets like 5% of the fee as well. It's a very lucrative business. That's why you got like 500K USD per day as the protocol fee. That's how they get it. So we mentioned before that the price of the share has a direct relationship to the number of outstanding shares. For example, if you have 10 outstanding shares, like right now Kobe has 10 like people holding the shares, versus like when there's like 100 people holding the shares, the price will grow like exponentially. And here is actually the exact formula to calculate the price based on the number of outstanding shares. As you can see, it's actually like exponential thing. For example, when you have like 10 outstanding share, you put 10 here and you get the price of this. And when it's 20, you have 20 to the power 2 divided by 16,000, you get this number. And one thing to notice is that when you sell a share, since the number of shares will decrease, right? So you will use, if for example, right now you have like 10 outstanding shares, if you want to sell one share, you will use 9 to calculate the sale price, because the number of shares will decrease to 9. Which means that it doesn't really make any economic sense for you to buy a share and then immediately sell it, because you'll then have a loss. And this discrepancy between the buy price and sell price is called a spread here. And due to the nature of this exponential growth in price to the number of shares, the spread in the very beginning will be very big. And as the number of shares grow, it will basically shrink, as illustrated in this graph. And if you draw the spread as a percentage of sales, you get this graph. Basically, it moves towards like 0. Basically, this column, and this graph shows that the price of each of the share grows exponentially to like in relation to the number of shares here. Basically represents this price formula. So yeah, this is basically the how the Friend.Tech works. Each of the participants, the platform, the subject, the fan base, like all the fans, each of them have an incentive to participate in this game. The platform, of course, they get the protocol fee. The subject, the crypto influencer or celebrity, basically gets like 5% of the fee for any trade of the shares among the fan base, right? So they get incentives to keep the fan base, so they can provide some exclusive access to some, like things that they offer. For example, like the chats, group chats, for example, some offline activities and so on, just to keep the fan base together. So it's like a social network with some kind of an incentive at play here. And for the fan base, you not only can get access to your like celebrity, your influencer, but also like you can buy early and sell later and make a profit. There's like a speculation going on there, and as we all know, in crypto, speculation is a pretty powerful force here. And all these forces basically makes Friend.Tech as a dApp a very, very popular like a dApp in the crypto right now. All right, so with this, let's probably take a look at the smart contract itself. So let's skip the owner part. Basically, this says that some of the operations can only be done by the owners, and you can transfer ownership and things like that. Let's go straight to the needs of the smart contract. So here we have like this event, which basically gets emitted when there's a trade. And the more interesting thing is that we have these two mapping. And the first one represents the balance of each of the holder for a subject. For example, if you are Kobe, in this case, it represents the balance of all your holders. Like each of the holder has a balance, right? So this nested mapping represents that. And then you also have a mapping to represent the total outstanding number of shares per subject. So this is important because it can be used to calculate the buy price and sell price according to this table, right? So these two mappings are quite important to keep track of the total number of outstanding shares and also the balance of each of the holder for a subject. So it's two mappings. And then we have a few functions to set the fee destination, set the protocol fee percentage and subject fee percentage. Quite straightforward. Only owners can set it. Right now, the protocol fee and the subject fee are both like 5%, but they can be set to different percentages, like if you're owner. And the next function is quite interesting as well. It's a get price. What it takes is the supply and also the amount that returns a price. So this basically, even though it looks quite complicated, but what it does is to calculate the price based on the number of shares here. Like the first one is the number of outstanding shares. The second one is how many shares you want to buy. So for example, if you the number of outstanding shares 10, you want to buy 3 shares, it will return basically these 3 values adding up together. You don't have to look into to understand all this, but you just need to know that this calculates like the total price based on how many like outstanding shares do you have right now and how many you want to buy. So in the case of 16 outstanding number of outstanding shares, and you want to buy 5, basically adds up this 5 prices together. Yeah, that's all you need to know. And then there's like 2 functions, get buy price and get sell price. These 2 functions uses this get price function and also this map. As we remember, like this map keeps track of the total number of outstanding shares per subject. So this gets the outstanding share, number of outstanding share for this particular subject, and then the amount you want to buy. Use this function to calculate the total price. And the get sell price does pretty much the same thing, except that it subtracts the amounts that you want to buy, want to sell, because after you sell the share, the total number of outstanding share will be reduced, right, by this amount. That's pretty much the same thing. And these 2 functions basically calculates the buy and sell price, and also taking like a protocol fee and the subject fee into consideration. So in the case of buy price, you not only have to pay the buy price, but also you have to add the protocol fee and subject fee. So in the end, you pay this much. Before when you sell the share, you don't get a full price of the sale price. You have to remove the protocol fee and subject fee. So this is the value, the amount that you got as a seller. Yeah. And then it's like the buy and sell share function. So these 2 functions at high level not only calculates the price and protocol fee, subject fee, but also moves this assets to the appropriate destination. For example, the price, the protocol fee goes to the protocol, the subject goes to the subject, the buyer pays the fee, the seller gets the fee, and so on and so forth. So this part involves the movement of the assets. We will talk about this in the next session of the workshop, since we can use it to demonstrate the asset permission system, since it involves the assets. And in this session, we will try to implement the rest of the contract. Yeah, so let's go. So we have a repository created for this workshop. That's here, and if you clone this repository, you'll realize that we have like two branches, session 1 and session 2. So in this session, we'll focus on session 1 branch. So I have cloned this repository and checked out session 1 branch. We structured the session 1 branch into 4 commits. We're going to go from the first commit to the last commit. Let's check out the first one. So let's see what we have here. We have a pretty minimalistic Friend.Tech smart contract with only one readable field. And we have a function to update the owner readable field. And only the current owner should be able to do that. Otherwise, it's going to throw exception with this error code. And after the owner is set to the new owner, it should emit the event. Looks pretty straightforward. And if you remember correctly, there's some code in the original like Solidity contract that deals with the ownership. It allows you to check ownership. It allows you to transfer ownership. So we're basically trying to re-implementing that. And we do have a control script for this to deploy the contract. And we also have used a transaction script to call this method. So if you don't remember, transaction scripts is almost like a main function for a transaction. It's like the entry point to call the smart contracts and so on. So here you not only can call just one contract, you can actually call multiple contracts and get the results and pass them around, glue them together, things like that. So it's a very flexible way to invoke smart contracts. And we actually had a pretty extensive discussion about that in the previous dev workshop. So if you need a refresher, you can probably go back and watch that. We also have written the test for this. There's a test called update. The owner should be okay. It looks pretty straightforward. Initially, it checks that the owner of this Friend.Tech contract is the same as the address of the deployer. Then it tries to set the owner with the wrong current owner, which basically triggers an exception. And if you set it using the right owner, the owner should be updated. So that's basically the logic of the test. Yeah, let's run it. So let's first on this. Then let's test this. All right, looks like it worked. So let's move on to the next commit. What do we have here? So if we look at the diff, it introduced, so other than the owner, it introduced 3 more readable fields. And we have 2 extra functions that basically updates this 2 field. If you remember from the original implementation, it has the protocol fee percentage and subject fee percentage. But here we have the same thing, and we have this, the same functions to update them, and only the owner should be able to do this. So that's pretty straightforward. But we also have introduced this value called total protocol fee. And this value, we don't have it here. And the reason is because there's like something called protocol fee destination in the original Solidity code. We don't have that. And the reason is because Alephium is UTXO based. So if we set a regular address as the destination fee, and every time when there's a protocol fee, we basically send to this address, that would create potentially a lot of UTXOs, which is not very efficient. So a better way to do this is to actually get a protocol fee into the smart contract, like the Friend.Tech smart contract, and then only allow the owner to withdraw them. So basically, the owner has the protocol fee. So here we have this withdraw protocol fee function. When the owner calls it, it basically gets all the protocol fee and sets this value to 0 again. Next time, when you accumulate enough protocol fees, you can call this again and withdraw the remaining protocol fees. So that's more efficient ways to do this. Nice. So yeah, this is the read contract. And the deployment script basically does pretty much the same thing, except that it sets the initial value for this 3 new readable fields. And the protocol fee and the subject fee are both set to 500 basis points. And if we look at the test, we have a new test called set fee percent should work. Basically, this verifies that the owner should not be able to update the protocol fee and subject fee. And once the owner updates calls this to function, they should be able to update the value of this. Then after this is executed, the state of the contract should be updated as well to, in this case, to 600. All right, so this looks pretty straightforward as well. So let's try to compile this. And then test this. Great, looks like it worked as well. Next, let's try to implement the feature to keep track of the share balances. If we go back to the original smart contract, we actually use the mapping data structures to do that. For example, here we have a nested mapping data structure to keep track of the balance for each of the holder for this subject. Here we have another mapping to keep track of the total supply for each subject. In graph, we actually don't have the mapping data structure. Instead, we have something called the subcontracts. And the way it works is that if we have a contract, given a key, we can magnetically generate or create a subcontract from that. And if you have a set of keys, you'll be able to create a set of subcontracts. And this resembles the shape of a map because we can go from a key to its value. And because subcontracts is just a contract, so you can use it to store like multiple values. So naively, you can view this as a replacement for a mapping and a struct. By the way, struct will actually be supported in graph in the future. And the reason why Alephium made this design choice is that we think that mapping could cause the state bloat of a single contract, because if you just have a contract with a mapping and you just keep adding stuff to it, you might end up with a contract with a very big state. with very little incentive to. But instead, if you use a subcontract, we create a new entry in this quote-unquote mapping structure. Probably will think twice because it's not free. Subcontract actually requires comfort deposit, which is set to like 1 ETH right now. And after you create this entry, you probably want to clean it up because you can reclaim the comfort deposit back. So you have the incentives to recycle the subcontracts to keep the blockchain lean. And also because the subcontract is just a contract, you can actually use it to issue tokens, issue assets, and manage assets. And all the fields in this contract, you can have fine-grained access control to them. And for the assets managed by this contract, you can have permission control to them as well. So it offers a lot more than just mapping plus struct. Another interesting thing about this is that you can not only refer to this subcontract using the combination of the parent contract ID and the key, but also, since this is just a contract, it has a contract ID as well. So basically, there's 2 ways to refer to this subcontract, which in some scenarios is pretty convenient. For example, in the case of MFP, we implement like one implementation is to implement an MFP collection using parent contracts, and the key is like just like an index, and then MFP is represented using a subcontract. So you can actually refer to MFP directly using the ID of the MFP contract ID. Of course, you can also refer to it using a combination of the collection ID plus the index ID. But sometimes it's a lot easier to just refer to it using the subcontract ID. And from the implementation perspective, it makes things a lot easier in the VM because everything is just a contract. So that's sort of the benefit of the subcontracts compared to mapping. So let's look at the implementation to keep track of the balancing rough. So that's the commit. This one. Actually, I draw a graph for this. So basically, right now we have a Friend.Tech smart contract, and one way to keep track of balance is that for each of the subjects, we can use the address of the subject as a key and create a subject contract called subject share. And in there, we have something. We have a supply. Basically, keeps track of the total supply for this subject. And then for each of the subject share contract, given a address of a holder, we can create another subcontract that keeps track of the balance of this particular holder for this subject. So we can have like this subcontract structure to help us to keep track of the balance of everything, which is exactly what we did in this commit. So we have implemented the subject share balance, which is here. It basically has a balance field, and then we have implemented the function to return it. Then we have a subject share contract, which is this, where we basically have a supply field, which keeps track of the total supply for this subject. And we have a function to get a balance for a particular holder. So here, we basically, if we know the address of the holder, we can check that, okay, do you actually have a subcontract for this holder? And if we don't, it means that this holder doesn't hold any share for this subject. And if it does, if this subcontract exists, we basically just call the getBalance function from this subcontract, right? So this is what this getBalance function does. It tries to calculate the user's built-in function called subcontract ID to calculate the subcontract ID for this contract based on the holder address. it uses holder address as the input. Then it tries to check, okay, does this contract exist? If it exists, then we're gonna call the get balance function from this contract. Otherwise, we're gonna return 0 because this holder doesn't hold any shares for the subject. So that's pretty straightforward, right? And then at the Friend.Tech smart contract, we have also introduced two functions. One is get supply, one is get balance. For get supply, it's kind of similar. So we check. So we check for this subject. We check whether this subcontract exists. Because if it doesn't exist, then the total supply of the subject is 0, right? If it does exist, then we can just return the supply. So if you look at the code, it basically calculates the subcontract ID using the same subcontract ID built-in function, and it checks whether this contract exists. If it exists, it calls the get supply function that we have implemented here. Otherwise, it returns 0. And for get balance, it's the same. It checks whether we have the subject here, subcontract for this particular subject. If it does, then we will just call the get balance function we implemented here. Otherwise, it just returns 0, since if we don't really even have this subcontract. And of course, it doesn't have any, no holder would hold any share for this because the total supply is 0. Yeah, this is basically how we keep track of the balance. You might wonder, like, where do we create this? And that will happen when we buy shares. And when we sell shares, sometimes we actually destroy some of the subcontracts. So we will investigate those in the next session. So this session, we basically just assume that, these things happen. And then if we have these subcontracts, these are the set of functions to help us to get the balance, get the supply, and so on. Great. So in the next commit, we implement the pricing. Let's see what we have here. If you go back to the original contract, it looks almost identical. This get price function and also this get buy price and the sell price function. So get price function looks almost identical here. Get buy function and get sell function in Solidity actually use this mapping to get the total number of outstanding shares for this particular subject. We used the get supply function that we implement in the previous commit that leverages the subcontracts to get the supply for this subject. Then we use the same get price function to calculate the total price for this amount of shares. So there's not much to talk about here. It's pretty much the same as the original thing. You can see that sometimes it's pretty easy to port the functionality from Solidity to Rust. It looks kind of almost identical. We also wrote tests for this. So as you can see here, get price for 0 is 0, 100 is this, and if you go to the spreadsheets, you can see that, what is the value of 100? It's a 0.625. And if you look at the 296, it's 5.4. So it means that if this test passed, then everything was implemented correctly. Let's try to actually run it. And test it. Great. So this means that the pricing function works as expected. So yeah, now I think we have finished implementing everything for session 1. In the next session, we will try to implement the buy and sell shares function in the original smart contract. We will also, because in these two functions, we also update the balances. Right now, we just try to get the balances. We'll try to, it will update the balance. So we will basically create and destroy the subcontract in this graph. Yeah, thanks so much for participating, for watching the video. I'll see you next time. If you have any questions, please feel free to ask in the Discord channel. Thanks.